Thank you.
It's
First of all,
okay.
I want to thank you for my invitation as a plenary speaker in this conference. I uh, I think I was my fourth participation in ICAS conference, and I'm sorry that it's online. Maybe the next will be not online. My presentation title is on the screen, and I will talk about photogrammetry, technique to create 3D objects. This technique, photogrammetry, is used in many particular fields, like you see in the left of the screen: archaeology, cultural heritage, forensic analysis, biology, and so on. But in this list of fields, the mechanical field is not so used. So my goal was to use this technique in mechanical fields. And also I want to compare some free and commercial application package used in photogrammetry technique. What is photogrammetry? It's a technique to extract geometric information from two-dimensional image or videos. Of course, the name is derived from Greek words: photos, light; gramma, letters; and metrein, to measure. Do you see the presentation? Hello.
Yes, everything is okay. Just continue.
Okay. Uh, so photogrammetry is the technique to take multiple overlapping photos and obtain measurement from them. To generate 3D objects. The basic principle is similar to the way many cameras create a panorama by stitching together overlapping photos into 2D mosaic. Everyone has a phone now and take many photos, many images to create a panorama. And the photogrammetry technique takes the concept one step further by using the position of the camera as it moves through 3D space to estimate the X, Y, and Z coordinates from each pixel of the original image. However, from several photos of the same object that were taken from different positions, a third coordinate Z can be extracted. So the required condition for every point to be visible in at least two photos. So knowing the geometrical parameters of the location where the pictures were taken from and the camera parameters, the three-dimensional coordinates that are located at the intersection of at least two view angles can be calculated. So in this way, information that is extracted from photos regarding the points can be used to reconstruct line, distances, areas, and volume of space. But to use photogrammetry, you need a photo camera or a phone. Recommendation regarding the acquisition of the image as very things to avoid: very dark surface, reflective surface, transparent surface, including water, uniform texture and solid color surface, moving light, and capturing your own shadows. So you can see in the left we have many good match blue between photos, two photos, two image, and in the right bad overlap, only 6 good match between two photos. So what are the steps of the photogrammetry? First step is acquire photos with a phone or a camera. Import photos into the software, align photos, and build sparse cloud. In this step, compare the pixel in the photos to find match, estimate camera location, and build a 3D geometry from them. A sparse point cloud is generated. The next step is build dense cloud. Once satisfied with the alignment of the camera, the sparse point cloud is processed into a dense cloud in which each matchable pixel will get its own X, Y, Z location in 3D space. Next step is build mesh. This step connects each set of 3 adjust points into a triangular face, which combine seamlessly to produce a continuous mesh over the surface of the model. The next step is build texture, scale the geometry, and export the geometry to a CAD software. It's an example of these steps. The object is a statue in the left upper side. The next step is take many pictures of the same objects. The next step, data processing with the software, and the final object, dense point cloud of this statue. There are some software that can be used in photogrammetry techniques. One of them is PhotoModeler, which have a bigger price, $2,300. It's produced from a company from Vancouver, founded in 1919. Other software is from an Italian company, 3D Zephyr, has many variants, a free version. He can process maximum 50 image per project. The light version process maximum 500 image per project monthly, with and perpetual license with a price of 4,200 euro. And this soft is produced by Italian company. This is an example of a Cathedral of Pisa reconstructed with this software. Another software is Visual SFM. It's a free software for personal use, non-profit for educational purposes. This is an example of reconstruction of the tire tracks. Another software is Adisoft Metashape, which is produced by a Russian company, St. Petersburg, Russian. This software can be used for aerial image processing, extractive industry, agriculture, architecture, visual effects, games. For this last software, Adisoft Metashape, this is a chart with required memory in gigabytes for processing the image. You can see that for exceptional quality and number of image 10,000, he required 640 gigabytes of memory. But is not required all the time to obtain this number of image. Of course, you can take 100, 200, 500, and according with the number of image, the quantity of memory is increased. This is an application of photogrammetry based on a sample cone. This cone has a diameter of 10 meters, and the was used by Paul Koffel for quality analysis to see if photogrammetry can be used in mechanical fields. The mean distance to the object surface was 4 meters. This is the distance where the camera was taken the pictures. Canon camera. and obtaining 800 points, comparing with lesser station. So we have a comparison between laser scanning and photogrammetry technique, and the results show that the precision of the model becomes worse in the inaccessible border regions due to the lower amount of photo information and poor illumination. So when you take picture, it's required a good illumination in this process. So the overall deviation of 1.3 millimeters show a reasonable accuracy of dense point cloud in accordance with the resulting model. I remember you that the cone has 10 meters diameters. So many years ago, I want to test this technique, photogrammetry, on a car hood. This was my first application with this technique. This is the position of the camera, photo, and I obtained over 1 million points on this car. I imported this car hood into rapid form software, and this application was done with Agisoft Meta Shape software. Was my first application to test if I can obtain a 3D geometry from photos. Another application was on Pelton bucket. You can see the Pelton bucket on the left, put on the chair in the right. The dense cloud I obtained 6 million points. And this is the texture model of the Pelton bucket. This application was also made with Agisoft MetaShape software. Another application was on a Francis runner in the company in Reșița City in Romania. This Francis runner with a diameter of 1,160 millimeters and has 19 blades. And this runner service over more than 50 years. You can see that the surface of the runner has some holes, and these holes appeared during the using time. This is the Francis runner, and the dense cloud for this runner I obtained over 18 million points. And you can see in the right that the 3D geometry of the runner obtained to this technique, photogrammetry. I take 133 image, and finally I have the drawing of the Francis runner generated in SolidWorks with green color. Another application is for a Kaplan runner blade. Also with Agisoft MetaShape, I generate the geometry. You can see the blade in industrial company. This is in this case I have a 3D model of this blade. So I have the project of this blade, and I wanted to compare the project with the geometry obtained through photogrammetry and see the difference between the project and the photogrammetry results. In this picture, you can see the cameras take the position of the cameras take around the blade. I obtain over 50 million points on the blade, and I have 43 pictures taken for this blade, and I have a calcul performed for several hours on a laptop with Windows 7. You can see the dense point cloud imported into geometric design software, the mesh created using geometric design software, the blade surface and the trunnion cylinders, and the profile that result from the blade intersection with cylinders. This is the solid format of the blade and SolidWorks software. And because I have the project of the blade and the 3D geometry obtained by photogrammetry, I wanted to compare the difference between them and in GOM Inspect software. We can see that the difference are between 1 and maximum 5 millimeters, but this blade has a diameter of 5 meters, 5,400 meters. So this difference are not so big for this huge dimension of the blade. Another picture with the difference between project and generated blade through photogrammetry. Another difference with and these are different of the profile. So the conclusion was the precision of a reconstruction done through photogrammetry depends on several elements. The quality of the camera and settings required for shooting, the number, position, and picture quality, the setting imposed on photogrammetry software. So increased accuracy can be achieved by having more experience in using the photogrammetry technology and the software associated with it. So this paper aims to investigate literature in the field of photogrammetry in order to answer the question of whether or not it can be used to reconstruct the geometry of mechanical components. So the results from the literature and personal experience convince the author that photogrammetry can be successful used in the field of mechanical engineering with a precision that is equivalent to 3D scanning technology, but an incomparably lower cost. Of course, scanning technique is more precisely, but a scanner cost very high, while a big camera is cost very low. So in the time I have in my presentation, I want to hello, do you hear me?
Yes, we can hear you.
Yes.
I want to exemplify the 3D Zephyr software. Can you see my screen?
Yes, we can see your screen.
Okay. First of all, I create a new project. Add import a picture and photos. I have a statue from a museum in Hungary. These are these photos. Okay. These photos are imported into the software. Okay, and next, he extract the parameter of the camera, which are saved in the photos. And now it's, I go to next step and run. There are a small number of photos, are only 8 photos, so the process will be very quick. And now he obtained the sparse point cloud. You can see the position of the camera with a blue color, and the sparse point cloud, it's can be viewed by points. The next step is to construct the tree model generation, dense point cloud generation. Next, and run. Of course, I can change the settings of the software, but is not the case now. So you can see the points, dense points generated by TradeZF software, and another step is to create to extract the mesh. Next, and run. The free version of 3D Zephyr software can be used only for maximum 50 pictures, 50 image. And finish. We can see the surface of the statue and the position of the cameras of the photo. I take this photo with my phone. It's not a super quality of the image, but you can see the results of the photogrammetry. Of course, this image can be changed, can be updated and corrected by delete some triangles that are not part of the geometry. Okay, thank you very much. If you have question.
Yeah. Do you have any question? If you haven't, please, I
stopped sharing my screen, and thank you for invitation, and thank you for to hear my presentation.